Hello everyone, I am Zixuan Wang, a PhD student at UC San Diego, and I'm working with Professor Jixian Zhao and Professor Steven Swanson. Today I'm going to present our paper, Characterizing and Modeling Non-Volatile Memory Systems. In this project, we build a profiler and a simulator for non-volatile memory and open source them on GitHub. In this presentation, I will first introduce the background of this project. Then I will introduce Lens, a profiler we build to characterize the non-volatile memory systems. And then Vance, a cycle-level simulator that matches the real non-volatile memory performance. And finally, the validation results of Vance. Now, let's start with the background and motivation. Non-volatile memory is a type of main memory that sits on memory bus and provides better addressable access to CPUs, just like traditional DRAM-based main memory. It also provides data persistence, so the data written into non-volatile memory can be recovered after a system reboot. The Intel Optane is the first commercially available non-volatile memory product, and we can buy it now. But when we are using this non-volatile memory product, we find some unexpected performance characteristics. For example, here is a performance comparison between DRAM and Optane. We observe that some workloads are slowed down more than the others. We want to find out the detailed reason behind these performance variants. So we want to use a simulator to understand architecture-level behaviors, such as TLB miss or overhead inside non-volatile memory DIMMs. But the problem is the existing DRAM-based simulators and emulators are not accurate enough. We compare the DRAM Sim2 and Remulator to Optane DIMM and find their bandwidth and latency are not accurate enough. We then compare the DRAM-based emulator with Optane DIMM. We find that using emulator, cacheable write bandwidth is higher than non-temporal write, while using Optane DIMM, cacheable write bandwidth is lower than non-temporal write. This motivates us to build a new memory simulator. But can we build a non-volatile memory simulator that is constantly slower than DRAM? The answer is no. Here is an example. We perform pointer tracing tests on Optane DIMM and PMAP, a DRAM-based non-volatile memory emulator. We find PMAP latency is stable, while Optane DIMM latency is not constantly slower than PMAP, which means the real non-volatile memory is not just a slower DRAM. It has complex controller designs, multi-level buffers, and unpublished DDRT protocol. So, to build an accurate memory simulator, we first need to know more architecture-level details. This motivates us to build a new profiler. In this project, we first build Lens, a low-level profiler for non-volatile memory systems. It has carefully crafted micro-benchmarks that trigger specific hardware behaviors and discovers complex microarchitecture design of non-volatile memory products. It also achieves low-noise profiling results. Based on Lens profiling results, we build Vance, a validated architectural non-volatile memory simulator. Vance performance is validated with Optane DIMM. It has verified DDR4 model for on-DIMM buffers and can be integrated to Gem5 for full system simulation. Vance provides a general non-volatile memory model that can be reconfigured to simulate other non-volatile memory products. Lens and Vance are open sourced on GitHub. Now, let's take a look at Lens design and its profiling results. Lens framework is built as a Linux kernel module to reduce kernel and user space switching overhead. It contains micro-benchmarks written in assembly code to maintain well-controlled memory access. It disables cache prefetching and uses non-temporal load and store instructions to bypass the cache. It also uses the AVX512 registers to emulate cache line granularity memory access. Lens runs micro-benchmarks on non-volatile memory using single DIMM and multi-DIMM settings. These micro-benchmarks discover the access latency, buffer size, write policy, and many other architecture-level details. Lens first uses a pointer tracing test to detect the undimmed buffer size and their access granularity. A pointer tracing test is a random-based memory access test. It divides a memory region into equal-sized blocks and accesses these blocks in random order. It uses sequential access within each block. Here is an overview of non-volatile memory system architecture. There are CPU cores and integrated memory controller. According to Intel's public documentation, there is a write pending queue inside integrated memory controller, although we do not know its size. And there are non-volatile memory medias on the DIMM. That's all we know from publicly available information. Now, we use a pointer tracing access test with 64-byte blocks to discover the buffer sizes. As shown in this figure, the x-axis is access region size, and y-axis is latency per cache line. We measure the read and write latency separately. In this test, the read latency starts to increase with 16 kilobyte region size, which means there is a 16 kilobyte buffer overflows at this point. We denote it as L1 buffer. For the same reason, there is a 16 megabyte L2 buffer. The L2 buffer latency is about 100 nanoseconds, which means it's inside a DRAM. The write latency starts to increase with 4 kilobyte region size. This indicates a low store queue on non-volatile memory DIMM that performs request reordering and write combining. The write latency drops until 512 byte region size, which indicates the size of write pending queue. Now we already know the buffer sizes, but some buffers may not use the 64-byte entry size. To detect the buffer entry sizes, we still use the pointer tracing test, but in a different way. This time we change the pointer tracing block size and measures the amplification factor in each buffer. Once the amplification factor drops to 1, that block size is considered as buffer entry size. The amplification factor is calculated as the ratio of the size of actually read-write data to the size of requested data. For example, if a 64-byte request leads to 256-byte data read into the buffer, then the amplification factor is calculated as 4. Here we use two examples to show how to detect buffer entry size with amplification factor. In the first example here, we use a small block size, which is half of the L1 buffer entry size. And the memory region is divided into 4 blocks, accessed in random order. For simplicity, we assume L1 buffer contains only one entry, and all the entries are already stored in L2 buffer. Now, CPU starts to access the first block. The corresponding entry is loaded into L1 buffer and sequentially sent to CPU cores. Then the second, the third, and the fourth block. In this test, the CPU accessed all 4 blocks, which is 2 L1 entry sized. But L1 buffer actually loads 4 entries, and this leads to an amplification factor of 2. But once we use a large block size that is equal to L1 entry size, the amplification factor drops to 1. Here in this example, we have the same assumption as the last example. The only difference is that the block size is doubled and memory region is divided into 2 blocks. Now, CPU accesses the first block, L1 buffer loads the entry, and sequentially sends it to the CPU. Then the second block. In this test, the CPU accesses 2 blocks, and L1 buffer loads 2 entries. This leads to an amplification factor of 1. Here we show the read amplification factor under different block sizes for L1 buffer and L2 buffer separately. We notice that L1 buffer amplification drops to 1 with 256-byte block, which means L1 buffer entry size is 256 byte. For the same reason, the L2 buffer entry size is 4 kilobyte. Here we present a write amplification factor for low store queue and write pending queue. The low store queue amplification drops to 1 with 256-byte block, which means it performs write combining that combines consecutive write access to one 256-byte request. This is to reduce the read multiply write procedure in L1 buffer. The write pending queue amplification drops to 1 with 512-byte block, which means the write pending queue size is 512 byte, and one mfence instruction flushes the entire write pending queue. In summary, we find the size of write pending queue is 512 byte, and it uses 64-byte entry size. The low store queue size is 4 kilobyte, and it uses 64-byte entry size. There is a 16 kilobyte L1 buffer with 256-byte entries, and a 16 megabyte L2 buffer in DRAM with 4 kilobyte entries. Next, we use an override test to detect the where leveling data migration details. This test repeatedly writes data to the same 256-byte memory block and measures the write latency of each 256-byte write. We find there a long tail latency happens every 4 megabyte write, which may be related to the where leveling mechanism in non-volatile memory DIMMs. Here is an example of how where leveling works. The CPU repeatedly writes data to the same memory media location, and this area is getting wear out. Then the controller in the non-volatile memory DIMM blocks the CPU write, migrates data to another media location, and redirects the following CPU write to the new location. This is similar to the where leveling on the SSD devices. To detect the data migration block size for where leveling, we perform override tests on different sized memory regions and measures the frequency of long tail latency. Here we notice that the long tail latency frequency drops to nearly 0 with a 64 kilobyte region size, which means the controller migrates 64 kilobyte data for each where leveling. In summary, our override test finds the data migration for where leveling or thermal control purpose. This migration happens every 4 megabyte write to the same memory location, and it migrates 64 kilobyte data every time. Here we use a sequential write test to detect the multi-DIMM interleaving scheme for non-volatile memory. We perform sequential write with different region sizes and measures the total execution time under each region size. We test the single DIMM and interleaved 6-DIMM settings. Here we notice that the write to the interleaved 6-DIMM shows a repeated latency trend every 4 kilobyte. This indicates that different 4 kilobyte pages are separated to different DIMMs. Now we present the design of VANCE. VANCE implements an integrated memory controller with write pending queue. It also implements non-volatile memory model with undimmed low store queue that reorders requests and performs write combining. There is a read modify write buffer, which we refer to as L1 buffer in the previous slides. There is an address indirection table stored in undimmed DRAM that handles the where leveling and address remapping. There is an AIT data buffer stored in undimmed DRAM, which we refer to as L2 buffer in the previous slides. Finally, we present how we validate our VANCE simulator. We verify the DDR4 model in VANCE using Micron DDR4 verification model with cadence toolchain. For non-volatile memory model, there is no formal verification tool, so we match the micro benchmark performance on the obtained DIMM. Here are the validation results using pointer chasing micro benchmark on single DIMM and interleaved 6-DIMM. We notice that the VANCE latency number and curves match the obtained DIMM very well. We also take the hardware counters from obtained DIMM and VANCE to calculate the read amplification for L1 buffer. As shown in the left figure, the amplification factors match very well. We then perform the override test on VANCE and find its long tail latency match the obtained DIMM. In summary, we first build Lens, a profiler that discovers the complex microarchitecture design of normal time memory DIMMs. Based on Lens profiling results, we build Vance, a normal time memory simulator that matches Intel Optane persistent memory DIMMs performance. Lens and Vance are open sourced on GitHub. This is our paper, Characterizing and Modeling Normal Time Memory Systems. Due to the time limit, we cannot present all the details. For more information, please read the paper. Thank you.